Hello everyone, my name is Paulo Arguelles. To my right is Dennis Viveros, Kevin Chaput, Steve Koenig, Dongling Li, and Yoshua Vasquez. We are the CubeSat design team, and this is our preliminary design review presentation. Today we're going to talk about our progress over the last semester developing our idea for a CubeSat mission payload. We're going to talk about some programmatic adjustments we've made, a risk assessment, and our technical progress. But before we do so, let me tell you a quick story. The year was 1577. A 6-year-old Johann Kepler looked out the window of his childhood home and saw a giant comet streaking across the night sky. Now he was young at the time, but nevertheless observant, for Kepler found that the comet's tail always points away from the sun. Well, this stuck with Kepler, and it eventually led him to believe that there must be some sort of wind in space. In fact, he wrote to Galileo, "Provide ships or sails adapted to the heavenly breezes, and there will be some who will brave even that void." 400 years later, we are still trying to figure out how to take full advantage of those heavenly breezes. We've conceived of crafts with giant solar sails relying solely on the photon momentum from the sun to propel them forward. Now at this point, you may be wondering, why are you talking so much about solar sails in a presentation about CubeSats? Well, one of our primary objectives is to submit a CubeSat mission proposal to NASA's Small Spacecraft Technology Program, or SSTP. And what they're looking for are teams that can demonstrate new small spacecraft technologies and capabilities for NASA missions. What we propose to do is to use a CubeSat as a technology demonstrator to achieve spacecraft controllability using solar sail-inspired technologies. Now, the term solar sail is often used in the context of spacecraft propulsion, and for good reason. In fact, it's a staple of interstellar missions. However, we believe that this technology has applications a bit closer to home. We posit that attitude control can be demonstrated on small spacecraft using solar sail-inspired technology. This is a largely unprecedented domain, and the literature behind this is very, very sparse. So we're basically starting from scratch here. But through our research, we found 2 ways that we can achieve this. The first way is by mechanical actuation, so by physically moving the solar sail vanes with respect to the incoming solar vector. That would create a net torque around the CubeSat's center of mass. And the other way to do it is through changing the reflective properties of the solar sail film, also to create a net torque around the center of mass. Now, for the purposes of our project, we focused our efforts on mechanical actuation for a number of reasons. As you'll see later on, this method is much easier to show on a test bed. And we're also able to create a simulation that proves that this method boasts twice as much angular acceleration as its alternative. But there's a huge problem we have to overcome when designing an experiment for this. We need to overcome the scaling problem. The forces we're dealing with are very minuscule, on the 10 to the negative 6 Newton level. And just to give you a sense of how small this is, picture an area the size of 2 football fields. Let's say that's your solar sail area. Now take a quarter and flip it onto the field. The force due to that quarter sitting on that field is the aggregate force being acted upon the solar sail in actual outer space. So we have no choice but to approximate these forces. And the way we've chosen to do it is to create a miniaturized laminar wind tunnel. The theory being that the air molecules bouncing off of the apparatus serves as an analog for photons bouncing off of the solar sail surface. In many ways, we're using classical billiard ball physics to approximate what is going on at the quantum level. And toward this end, we've split our group into 2 teams. The first team is called the testbed team, and they deal with verifying our solar sail as attitude control hypothesis using experiments. So they have a more data-driven approach. Whereas our simulation team has an objective of verifying our thesis fundamentally, using fundamental physics and kinematic equations. And to talk more about this programmatic change and others is Dong.
Thank you, Paulo. Hello, my name is Dongling Li. Today I'm going to talk about programmatic. Next slide, please. As the semester approaching to the end, we deliver a lot of items. such as 11 agenda minutes and 1 system requirement review, etc. At the same time, we made a lot of changes for coordinating the objective of our projects. As Paulo said, our objective is to submit a proposal for CubeSat missions that shows new small spacecraft technology. First, we learn about what is CubeSat, what's in the CubeSat, what do they do, and how do they work. And secondly, we research about the latest design of CubeSat that attached with the solar cell that work as a propulsion system. So we wonder, why couldn't we use it as our altitude control? And yes, we can. And the following question is, how can we simulate the space environment? Utilizing the wind tunnel. Next slide, please. Our organization divided into 4 groups. The first group is testbed group, which objective is to build a wind tunnel that generate big wind that blow onto the solar cell panel to test if it's there or not. The second group is simulation group, who verify the calculations by using Simulink. And the third group is administration. Its objective is to manage individual work properly. And the fourth group is counseling group. They support for the whole team. Next slide, please. These are the 6 main items we are going to deliver throughout the year. We have agenda minutes, preliminary design review that we're doing right now, 1 final report for fall and spring, 1 final design review, and prototype test bench. We are looking forward to working on it. Next slide, please. As you can see, we are on schedule so far, and we are ready for the next phase. Now I hand to Yusua, who will talk about system requirements.
Hi everyone. I'll be going over the system requirements. However, before I begin that, I'd like to take the time to focus our attention on what hones and tailors our project to be what it is. So if we go to the next slide. At the very top, we have the size and mass. Every U, which is a CubeSat, is to be no larger than 10 by 10 by 10 centimeters, and mass of no more than 1.33 kilograms per U. Another one is at the bottom is NASA Inspire, which is a way in which we can solicit research opportunities through NASA. And from that comes the Small Spacecraft Technology Program, which has its own requirements. If we go to the next slide, I'll go a little over that, which is TRLs, which is NASA's way of gauging the maturity of the technology. We have TRL 1 all the way to 9, and 9 being the most mature. If we go to the next one, I'll go over TRL 3, which is what we're doing, is showing proof of concept through analytical and experimental data. And on the next one, I'll begin the functional requirements. Our team of electrical engineers have been able to do some analysis on the power consumption that we do, which is less than 8 watts, bus voltage of 12 volts. And as far as mass and dimension, because it is a 3U, mass will be 3.99 kilograms, and the dimension is 10 by 10 by 30 centimeters. On the next slide, we'll go over our environmental requirements, which is altitude. We initially started at lower, but we're starting at 900 kilometers based on atmospheric drag. It'll make it a lot easier for us to steer. And maximum of 2,000 kilometers. And temperatures of negative 20 degrees Celsius to 50 degrees Celsius. Next is Steve, going over our progress overview.
Thank you, Yusua. I'm Steve. Today I'll take us through the progress on an overview of our progress on our project. As Paulo mentioned, there's been a shift in what it is we're doing, what it is we're designing for our CubeSat. Next slide. And so, before I go through that overview, it's important to go over the fundamentals of the CubeSat itself, and just keep in mind the requirements that Yusua went over, and some of the subsystems that our payload will need to interface with. For example, the command data handling system is one of the most important subsystems of the CubeSat. We will probably use a remote controller for our test bed, but that will evolve into a microcontroller maybe eventually a computer. Our telecommunication system, we pretty much narrowed that down to radio frequency. This is a very reliable and low-cost system commonly used in space missions. Telecommunication, electrical power system, power management, and distribution system. Most of these are components off the shelf, technology radio levelness TRL9, and thermal control system. We may even rely on the solar sail itself to use as a thermal control system as we use it for attitude control. Next slide. The payload itself, of course, is a very important part of this architecture. Keeping in mind the structure as a subsystem that has to fit in very efficiently. Propulsion itself may or may not have, we may rely on the solar sail for propulsion. But most importantly, the attitude control system, which will, of course, hopefully solely be controlled by the solar sail. We'll still want to rely on some of the more mundane components for GPS tracking and tumbling and stability of the spacecraft and deployment. So those systems we need. We may want to do away with the reaction wheels and magnet torquers and hopefully just rely on that solar sail for attitude control. Next slide. So now that we've gone over those kind of fundamentals of the subsystems in CubeSat, we want to start to go over what it is we're actually doing for our project, the solar sail, for the purpose of attitude control in low Earth orbit. We really want to take a deep dive into the science and theory behind solar sails. There's a ton of it out there, and we want to build a really solid foundation so that when we start to do the quick, as Paulo said, pool table physics and back to the analytical math, we can really start to produce some meaningful numbers. We got the characteristic acceleration, super important, incorporates the thrust of the solar wind and the density of the spacecraft, aerial density as well, the area of the solar cell versus the mass of the vehicle. So these are all, we soon realize it's also a aerodynamic problem, an aerodynamic challenge. You would have thought in outer space is an aerodynamic problem. So we want to definitely analyze those aspects. So we start to go to the whiteboard. This is a great place to start to do our rigor. Something about doing it on the whiteboard as a team really helps us produce some meaningful results to start to develop our test bed. So we've got some simple notional calculations for that using mass, conservation of mass and flow rates. Next slide. And so we begin to develop our test bed, just a simple single degree of freedom, single paddle design. To see if it even works, we soon realized that the fan just wasn't big enough. There's no wind. You couldn't really get any meaningful data out of there to even produce a single degree of freedom system. So we quickly went to 2 degree of freedom. We sketched it up, added it, and actually made this thing. But still, maybe too much turbulence. We wanted to refine it, see better, make it more aerodynamic. And so you can see our design is starting to refine. We realized, like I said before, that the fan was just not producing enough power. We need to go bigger on the fan. But we wanted to simulate this. So we made a CAD model with some simulation just to kind of visualize its feasibility and see if it works. This can actually spin around the z-axis as well in a more like later down the road multi-degree of freedom control system. And so the challenge with the fan, we went bigger and bigger. We realized it doesn't matter how big you go on the fan, it's just not designed for this. So Kevin will bring us to the details on why that happened. But we eventually got it working. We got our test bed going with some paddles, and we got some movement there, and we got the wind we want. Still needs to be further tested, but at least we have some motion here. Actually, yeah, that might be a little bit high speed. It actually goes a little slower than that, but we can reduce that. We can valve it and move a panel and produce less thrust on it. Maybe constrain it at the z-axis, but yeah, further testing will definitely have to be done. And eventually we get to some meaningful results, some data acquisition, some meaningful numbers. We want to quantify that, and maybe using the scientific method, these observations, do some question asking, like, what does this mean? How can we characterize this, and how can we predict it, and then maybe formulate a hypothesis and either refute or reject it with further testing. And well, hopefully the end result will be a simulating control system that will show this actually works in space. In LEO, we can put these panels out there, and with the forces and the scaling, have a starting with a single degree of freedom system, like I mentioned, evolve it into a multi-degree of freedom control system. Next slide, and ultimately bringing us to what it is we're trying to invent here. A solar sail capable of attitude control, maybe louvering panels, maybe an accordion deployment approach on that. So to go into further detail about that, I'll hand you over to Kevin to take the wheel and give us those details.
Hi everybody, I'm Kevin and I'll be getting into the mechanical design details. So here's what the inside of our test article at the test section looks like. Currently it's being strung up top by a fishing wire, but also some other designs to be considered are having magnets with opposing poles repelling each other, and possibly using air bearing tables and balancing it on a needle. We're looking for minimal to no frictional forces affecting the rotation. And so this is just a look at our third iteration. We have two other ones I see that talked about that have been produced good results. This one is using a 30-inch industrial pedestal foam. The issue with this was the fan diameter was too large of a bell mouth shroud had to be built around it and connecting to the foot, and you had to include there was a motor and a stand also on the back side of it, so building around that was difficult in order to prevent losses. And so typically fans are usually meant to be used on the section. They're usually blowing air at something. And you can obviously test that by putting your hand on the back side and front side. So it was really difficult to get low wind speeds, and that's due to the fan blades and the angle of attack of the blades. And so that led us to our fourth iteration, currently with the air mover fan. You can see here in the middle we have empty toilet paper rolls used as a screen to promote uniform airflow, but those will eventually be replaced by honeycomb, smaller honeycomb. And this is the completed wind tunnel with that air mover fan, the 8-inch diameter air mover fan. And so now let's look at the components. After we demonstrate proof of concept, we're obviously going to need a payload to implement the technology into. So now we'll dive into some of the components. So here you have the Mylar, and you have Mylar on the left side, which is a polymer blend material, and your Kapton and CP1 are imide polymer blends, which have a higher heat tolerance, and all of these just vary slightly in their chemical makeup. And so for our application, we determined that the aluminized Mylar would be the best fit due to its thinness and lowest density out of all three. And looking at the booms available to us, there is the triangular rollable and collapsible boom. And this, when it unfurls, it takes on the rectangular shape. And on the right side, you have a collapsible 2-mass, which when it unreels, it takes on a lenticular shape. And both of these are tightly wound on a reel, and as they deploy, they take on their respective shapes. And Air Force Labs did testing on each shape and determined that the track boom has a higher second moment of area, which is basically a measurement of a cross-sectional area's resistance to bending due to loading. And so based on some of that information, we decided that we'll most likely be going with the track boom due to its compact size and lesser mass. And so now looking at the design of the CubeSat itself, this is one option where we'd have rectangular sails on the sides And however, the issue with this, the challenge with this would be that about 3 sides would need to be rigidized, and that will be extremely difficult at this moment. And if upon our research it's determined that this is unfeasible, then we'll likely look towards other scale geometries, such as this one, where you have 2 panels on the sides of the CubeSat that would unfold, and you have some telescoping booms and constant force springs that would deploy simultaneously, unfurling the sail. And the constant force springs allow tension to be applied to the sail, and it exerts a constant resistance to uncoiling, which helps rigidize it. And so here we have a variation of that with the 2 panels on the sides. However, this one you have a mast this one will start with a mast in the middle and with the sail membrane wrapped around it, and that would unfold accordion style. And once it locks, it would rotate and work with the booms and springs to simultaneously deploy and unfurl the sail. Now the advantage of this would be the throttling capability of the mast would essentially allow change in sail area depending on if you need more torque or less torque. But one of the big challenge of this would be trying to prevent the sail from getting pinched during the winding and unwinding of the mast and ripping, which would obviously be catastrophic. So built on those 2 designs, this is what a possible 4-panel design would look like. You'd have 2 extra sails on the top, and that would allow for rotation not only about the z-axis, but it would help rotation along the y-axis as well. And now heading off to Dennis to talk about the electrical design details.
Hello everybody, my name is Dennis. I'm doing electrical design details. Here we have a diagram of the attitude control, the way the attitude control system is going to be wired. We have the paddles on the side coming out of our CubeSat in the middle. And for visualization purposes, we put the servo motors on the outside of the CubeSat. In reality, they actually be on the inside of the CubeSat. And these servo motors are connected to an Arduino, which will then be connected to our laptop for provide power. This is just our test setup. In our actual flight model, we'll have the Arduino actually housed inside of our CubeSat connected to an onboard power source. Here we take a closer look at our servo motors. They're actually micro servo motors. They weigh about 9 grams each. They're very small. It's very difficult to send something to space with a lot of mass and size, so we're very conscious of being as small as possible. These servo motors also have a rotation angle of about 180 degrees, which might seem like not a lot, but it's actually more than enough since we're rotating a maximum of 90 degrees. Here we conducted a small trace setting between the FS26 RC controller and the Arduino main. With the RC controller, it comes with small receivers that we're able to connect our servo motors to. This is actually very helpful for us because it reduces the need for wiring, and it will also give us full control of our servo motors right at our fingers on this RC controller. Now the downside to this RC controller is that we can't program it using MATLAB or Simulink or any other type of program like that. Which, since we can't program it, we're not able to automate it. Since we can't automate it, we won't be able to use this with it on our flight model. Now the Arduino Mini, we actually do need to do a bit of wiring and we do need to do a bit of programming. But once we do that, we have full control of our servo motors. And since we are able to program it, we won't be able to automate this process. We'll be able to automate this process. And due to this information, we'll be using the RC controller for our testing inside of our lab, and Arduino Mini for our presentation. Very close look at our Arduino. As you can see from the specs, it has a variety of input and output pins, which will be helpful for us because not only do we have the servo motors that we our paddles to worry about, but we actually have to worry about other electrical components inside of our CubeSat that need to be controlled as well.
And with Arduino, it's very small, so it actually helps us keep the size of the weight down for our fun. Here we have a simple circuit that we are able to control a servo motor using a potentiometer. This is interesting because you can actually swap that potentiometer out for a type of sensor. And with that sensor, we're able to actually automate this whole process and have the CubeSat keep its own orientation while in space. Here we have a simulated model that actually calculates the angular position, angular acceleration, and angular velocity of our CubeSat. Now in this model, we have our paddles configured to one being perfectly perpendicular to the solar wind and the other being perfectly parallel to the solar wind. Now in this configuration, it actually produces the maximum amount of torque, which will give us the maximum amount of angular acceleration. On this side, we have three graphs: angular position, angular velocity, and angular acceleration. Now in each of these graphs, we have two curves. The yellow curve represents our mechanical actuation method, and this blue curve represents our reflectivity chain, the reflectivity chain method that other spacecraft might use. As you can see, our mechanical actuation method actually yields much greater angular acceleration than the reflectivity chain, which will then give us a much higher angular velocity over time, which then will be able to change our angular position much faster. And with that, I'd like to hand it back to you.
So I'm back with risk assessments, and I'll go over technical and the schedule risk. We're mainly concerned about medium, high, and high, which is fan failure, which has happened already, but we're able to fix that. And then we also have sensor failure, communication failure, and hardware-software interface issues. Our mitigation approaches will be breadboard testing and frequent simulation testing. And on our next slide, I'll go over the schedule risk. Our wind tunnel, these are medium. Wind tunnel is done. We might have to make a few modifications on velocities or anything else. And as far as change in requirements and project scope, highly unlikely, but hopefully it doesn't happen because it would be give us serious consequences for our project. And as far as overview of our risk, as we've been able to manage to stay away from the severe area. Most of them are unlikely when possible. So our project is, as far as risk, is looking pretty good. And next, I'll give it to Apollo for our summary.
Thank you, Spark. Overall, our project prognosis is looking pretty good. We are on schedule with everything, and we have no foreseeable cost-related risks. Also, our simulation outputted results that were consistent with our hypothesis, which is always a good sign. In summary, our achievements this summer include creating a simulate graphical user interface where we can enter angles and solar sail size and also distance from the sun, and it'll give us angular response plots. And from those plots, we found that mechanical actuation is more effective at producing attitude control than the alternative. In fact, when we compare our simulation numbers to a real-life example of solar sail attitude control, which is Icaros, we see that our numbers compare quite favorably. Icaros was able to achieve a degree of change per day, but we project that we can achieve a degree per half hour. Our testbed team has finished with the miniaturized laminar wind tunnel, and right now we're working on making sure that the test articles being put in the wind tunnel give us optimal results for what we want to see. And our objective next semester is to outfit this with an autonomous closed-loop feedback control. So folks, what we presented to you today is not so much solar sailing as it is, and we're going to invent a new term here, so get ready, solar steering. And when you combine this technology with the mobility of small spacecraft and CubeSats, well, the possibilities are endless, both for our planet and beyond, wherever Kepler's heavenly breezes take us. Thank you all so much for listening, and let's take some questions.